Oh, can you hear me?
Yes, yes.
Yes. Okay. Yeah. Very good. I'm ready. Let me go ahead and share my presentation here. Okay.
Okay, so our next talk is by Kahmeyer, if I pronounce it right. Homotopy invariant of image as simple fold maps to oriented surface. Actually, I don't completely understand the meaning of the title, so maybe you can explain.
Yeah, sure. So again, this is joint work with Rustam. And first, I wanted to thank the organizers for inviting me. I'm very honored to be a part of this event. And so I'm going to be talking about a homotopy invariant of image simple fold maps to oriented surfaces. And so I need to define what image simple fold maps are. And so I would like to do that first. I quickly need a review of singularities. So let's let M to N be a generic smooth map from an M manifold to some surface. Let's remember that X is a regular point of the map F. If locally, it just looks like projection onto the first two factors. X is a fold singular point. If locally, when we map it, it looks like this difference and sum of squares here. And the index I in this sum is referring to the index of the fold singular point. And so if I is equal to 1 or M minus 1, I'll refer to this as definite. And if it's otherwise, I'll refer to these folds as indefinite folds. We also have cusp singular points here, which locally in coordinates, they behave like this. We're more interested in the geometry of them. So here's a picture on the left-hand side. I'm looking at a neighborhood of a fold point and a map of a surface to a surface. And you can see this is an example of a definite fold. On the left-hand side of this fold critical point, if I were just looking at like kind of projection here, orthogonal projection, I have regular values on the left-hand side of that curve in the image, but I do not have any critical value or any regular values on the right-hand side. So that's a definite fold. The picture on the right here is an example of a cusp and indefinite fold curves, because you can see on either side of the fold curves, I have regular values, right? And then the blue point there indicates the cusp where two fold curves kind of merge. And so the singular set of a generic map to a surface consists of fold and cusp points. And these are smooth closed one-dimensional submanifolds of the source. And I'm going to refer to the number of connected components of the singular set by this putting bars around sigma. In general, we're looking at when you restrict a map F to sigma, you have an immersion with double points and cusps. And so we'll refer to the set of self-intersection points or double points by delta of F. And then we'll refer to the set of cusp points by A2 of F here. And so now some definitions that'll maybe help the title make sense is if we have no cusps, that is to say if A2 is empty, then we'll call F a fold map intuitively. And then if delta is empty, we'll say F is image simple. And this definition is due to Osamu Saeki in his forthcoming paper. And so I wanted to remain in alignment with that. And so we're interested in image simple fold maps, which means the singular sets are smoothly embedded. And basically, I'll just have some number of copies of disjoint union S1s, right? So this is what the singular set looks like for image simple fold maps. And the homotopy invariant that we're interested is going to come from looking at the number of connecting components of sigma for image simple fold maps. So, i.e., the number of copies of S1 that we have. And we're looking for a homotopy invariant, which means we need to be able to modify sigma via homotopy. So let's take a look at how we can do this. Besides isotopy, there's a list of quote unquote allowable moves that we can perform. So the first one is a Reidemeister 2 move. And this is different from the not theoretic Reidemeister 2 move, right? Here we're actually introducing double points because this is, I'm looking in the target space here, and this is R2. So there are actual intersections here. So I'm allowed to create or cancel 2 pairs of double points. There's a Reidemeister 3 move, which takes a fold curve and it passes it through a double point. So for a slight moment, for one moment in the homotopy, I have a triple point. If you're thinking about the homotopy as a map with singularities as well. We are allowed to pass a cusp through a fold, and this is what I'll call a CF or a cusp fold move. And here I'm indicating index of my fold curve, like I was saying earlier. So for 2 fold curves that are joined at a cusp, they have to be of increasing index. So we'll always go from I to I plus 1 when locally we're looking at a cusp like this. And the direction is to indicate with what direction I'm taking index with respect to. If I were to flip the direction of this arrow, that would correspond to swapping the number of plus and minus signs in my formula for fold points. And so if I were to flip the arrow, this is the notion of relative index of a fold. I could talk about absolute index by taking the minimum of I, and then I think if you flip the signs, it would be m minus I minus 1. But so I'm going to talk about relative index and indicate the direction. So we have cusp merges as well, which allows us, if the indices line up, you can see I have 2 cusps neighboring each other. If the indices line up, then I can perform this merge, or in certain circumstances, I can unmerge. We're allowed to wrinkle our singular set, which means we start from with regular values. And then with regular values, we perform a wrinkle, and we get this kind of this component that looks like an eyeball here of 2 cusps and then fold segments of index I and I plus 1. We can also perform a swallowtail move, which introduces 2 cusps and a double point and a fold segment of I plus 1. So again, these 6 moves, along with isotopy, are what our singular set can undergo when we're performing homotopy. So I want to give a little bit of motivation for why we want to study the number of connected components of image simple fold maps. And this is due to a construction presented by Saiki in his 2018 paper, Elimination of Definite Folds. So for each homotopy class in Pi3S2, right? We know this is isomorphic to Z. We can construct an image simple fold map such that the number of connected components is precisely 1 more than the Hopf variant of maps in that homotopy class. So let's look at kind of the base case, or the easiest case here, when n equals 1. We have the Hopf fibration, which is S3 to S2 fibered by S1. It's known that the singular set of the Hopf fibration is empty. And we can wrinkle this Hopf fibration, and we get our I component here of index 0 and index 1 critical points. And so there's an index shift in my pictures. So I apologize. There's an index shift in my pictures from my formula. Here I'm referring to index 0 as definite. So index 0 would be definite, index 1 will be indefinite here. And then once I have this wrinkle, you can see I could perform isotopy to move these 2 cusps kind of very close together and then merge them. And if I merge them, I now have an image simple fold map with 2 components, which is 1 more than the positive Hopf fibration. And so how could we do this for general? Like if you just pick a representative of the homotopy class in here for Pi3S2. In general, if we take the connected sum of n copies of this wrinkled Hopf fibration appropriately, we can get a image simple fold map with n plus 1 number of components and Hopf invariant n, right? We know that the Hopf invariant, or excuse me, the Hopf fibration generates Pi3S2. So when we take connected sum in an appropriate way, we know that we're going to end up with a map that has Hopf invariant n. I need to be a little careful about the type of connected sum I'm taking here. I could take the connected sum of a bunch of 3 spheres and not end up with this singular set, right? So it needs to be in an appropriate manner such that, like, my attaching spheres, when I perform surgery, the definite folds are all surged to make a single component, right? And so now Saiki poses this question. He says, okay, well, if I pick any other map in that homotopy class, is it true that mod 2, the number of circles or the number of components of some other image simple fold map representative, is it true that this n+1 is preserved mod 2?
In this question, the target and source are not important. Any example are variant, yes? So
so in the question Saiki poses in his paper, and the answer to this question is specifically still for maps from S3 to S2. In a little bit, I'm going to talk about generalizing this. But right now, these maps are still, I'm still talking about image simple fold maps from S3 to S2. So the answer is no, and Rustam and I looked at this problem a little bit and actually had some conversation with Saiki. And it turns out we were looking over his paper, a signature invariant for stable maps of 3 manifolds into surfaces. And Saiki kind of found a counterexample without even really knowing it. And I want to go over that counterexample quickly and then move on to the generalization. So there's a collection of a wrinkle and a swallowtail move that I'm going to use here for this counterexample. And I call it a bow tie move because the result kind of looks like a bow tie or maybe an hourglass, depending on how you look at it. But so if we start with the empty set and wrinkle it again, and we get this I component, this wrinkled component, on the one fold up here, we can perform a swallowtail move, right? And that would introduce 2 cusps. That would introduce 2 cusps and a double point here. And this should be of increasing index. So my relative index would be 2 if my arrow was pointing upward. But for maps of a 3 manifold to a 2 manifold, 2 pointing up is the same as 0 pointing down, because if I swap the number of pluses and minuses, then I'm exchanging a definite fold for a definite fold, so it's no problem. And so here's the counterexample. Let's just start with mapping S3 to R2 by orthogonal projection, and then including that into S2. And we know the singular set of that is going to be 1 smoothly embedded component of definite folds, right? And so you can see this has 1 component. I'll perform this bow tie move 3 times on the inside of this circle where the regular values are occurring. And so I have these 3 bow ties. And I've dropped keeping track of the index here, but it's a very easy exercise to verify that the indices line up in the red dotted lines that I'm indicating. And so we can perform a cusp merge 3 times. And if we perform a cusp merge 3 times, again, each of where I've indicated, then we have a singular set that looks like this, with 3 self-intersections and 6 cusps. Now we can perform a Reidemeister 3 move or an R3 move and take this fold component and pass it up through the double point, creating a triple point for 1 moment in time. And now I have 3 swallowtail moves that I can undo. So I'll reverse flip here, here, and here. And what I'm left with on the inside is now a smoothly embedded component. So I found an image simple fold map with 2 components, homotopic generically to an image simple fold map with 1 component. And so Rustam and I asked the question, is this true in general? Are there any circumstances where maybe this parity is preserved? And so this is the question Rustam and I sought out to answer. And so our main theorem addresses some circumstances, at least. Hopefully someday we'll know all of them, but for now, there are at least a couple cases that are open. But for maps to surfaces, we have a partial answer. So let's set the stage a little bit. Let's say M is a closed-oriented manifold of dimension at least 2. F is an oriented surface of finite genus. And I'm looking at F and G to be homotopic image simple fold maps. So the idea here is I start with an image simple fold map, and I end with an image simple fold map. So the beginning of my homotopy and the end of my homotopy, those singular sets of those maps must be smoothly embedded. However, the homotopy between them could be arbitrarily complicated, at least within the moves and that we're allowing in isotopy, right? So there can be self-intersections, there can be cusps, there can be whatever you'd like in the homotopy itself, but what you start with and what you end with must be smoothly embedded. And our theorem says that the number of components of the singular set of image simple fold maps is a Z mod 2 homotopy invariant, provided at least one of the following conditions holds. So if the dimension of M of the source manifold is even, then this result holds. If the dimension of M is odd and no Reidemeister 3 moves occur during homotopy, then we have our result. And I don't know if I can go backwards here. There we go. So what it ends up turning out is it's this Reidemeister 3 move right here that caused problems. I don't want to use the word obstruction in the topological sense of obstruction, but loosely you could think about this Reidemeister 3 move as being the obstruction to this being this parity being preserved. For M equals 3, we will allow the target to be any oriented surface of finite genus. For odd dimension of 5 and higher for the source manifold, it's still open whether this is true or not for non-zero genus surfaces. And so for when M is not 3 in the odd dimensional case, I restrict that our target surface is a genus 0 surface, R2 or S2. Lastly, we have that the parity of components is preserved if the singular set of the homotopy is orientable, right? And so a homotopy between F and G is also a map itself. It's a map from 1 plus the dimension of your source manifold to R3 or to a 3 manifold, right? And so the singular set is going to be a surface in this case. And if the surface of that homotopy of the singular set is orientable, then we have our result. So what I would like to do for the remainder of the talk is go over a sketch of the proof. And to sketch the proof, we need two main tools. We need this notion of a chessboard function, and then we need the notion of the cumulative winding number for our singular set. So let's talk about chessboard functions. For chessboard functions, I'm going to be looking at smooth generic maps of non-negative dimension, i.e. M is greater than or equal to N. And then I'll define a chessboard function, an integral chessboard function, to be a locally constant function on the regular values of my map. And so, and for chessboard function, I require that for any two adjacent regions, i.e. two regions of regular values that share a border of fold components, I require that the value of the chessboard function differs by precisely 1. And so this may seem kind of like abstract or arbitrary at first, but there are some very crucial examples that are dependent upon the topology of regular fibers. So I'll get to some examples in a moment. We can also talk about Z mod 2 valued chessboard functions. For Z mod 2 valued chessboard functions, we basically just to each region of regular values, we assign a 0 or a 1. And you can always construct a Z mod 2 valued chessboard function from an integer valued chessboard function by just taking the values of the integer valued one mod 2, right? Okay, so once we include the data of a chessboard function to our singular set, we need to understand what happens at double points. And this will come up in the proof of the theorem, but I'd like to talk about it now. So up to cyclic permutation, there are only two types. We say a type of double point. And by a type of double point, I mean the double point as well as the information about the chessboard function around it. So there are up to cyclic permutation, there are only two types of double points. and we denote them as A minus 1, A plus 1, and then A plus 1, A plus 1. And so you can convince yourself pretty quickly that there are only two possible types, given that adjacent regions must differ by only one, right? So for example, if I was to assume the rightmost region has a value of a chessboard function of A plus 1, and that's maximal, without loss of generality, assume that that's maximal, well, then the top and bottom regions are forced to be A, right? Because it must differ by 1 and it has to be less than A plus 1. And then for the leftmost remaining region, this can be A minus 1 or A plus 1. And so again, this all may seem quite abstract and not sure how it will apply now, but when I get to the proof, it'll make a little more sense. So I think what is very important is to go over some of these examples of chessboard functions that are the values of C are determined by the topology of the fibers. So let's look at for an example, let's say we're mapping an n+1 manifold to an n manifold. We'll define the chessboard function to be the number of components of the fiber over a regular value y. So I'm kind of proving that this is a chessboard function by example, right? As far as proof by example can go here. Let's say I pick a regular value along this curve gamma. You can see the pre-image of gamma over here is this surface. If I pick the pre-image of, say, a regular value down here, then let's say that the inverse image is just one circle here. So the number of components in this region is 1. If I cross a fold curve of index 0, I know with respect to like Morse theory, that corresponds to attaching a handle of index 0. And so you could see once I cross this fold curve now, the inverse image of this point is 2 circles, right? And so the number of circles has changed by precisely 1. So the value of the chessboard function here would be 1. The value of the chessboard function here would be 2. And then you can see if I cross a fold curve of index 1, that corresponds to surgery of index 1, or attaching a 1 handle, right? And that would bring two circles together to get one component again. And so you can see this kind of, each time you cross a fold curve, you're performing oriented surgery. So this is where the orientability restriction comes in, right? Otherwise, in the non-orientable case, you could have you could pass a fold curve but not change the number of components. So this is an example for maps from n+1 to n manifolds. Another, yeah.
On your previous picture, what does the left-hand side correspond to on the right-hand side?
Yeah.
The red curve?
The red curve is gamma. And then over here, I'm looking at the inverse image of the entire curve. So does that make sense?
Yes.
Okay. Another very important example is if we're mapping an n+2k dimensional manifold to an n manifold here, we'll let n be at least 2 and then k at least 0. We can define the so-called Euler chessboard function, which takes values, the value of the chessboard function is determined by the Euler characteristic of regular fibers in that region. So if the Euler characteristic of the regular fiber is even, we divide it by 2. If it's odd, we add 1 and divide it by 2. And so I wanted to give a picture when we're mapping a 4 manifold to a 2 manifold here. Let's say well, in this context, regular fibers are going to be surfaces, right? Let's say the inverse image of a regular value y1 is the fiber is just S2. Right? This has Euler characteristic 2. So when you divide it by 2, the value of the chessboard function would be 1 in this region. And as I cross the fold curve of index 1, this corresponds to attaching a 1 handle, right? And if you attach a 1 handle to a sphere, you get a torus. The torus has Euler characteristic 0. Divide by 2, you still have 0. So the chessboard function in this picture would go from 1 to 0. You can see it differs by precisely 1. Again, this isn't proof, but it's kind of understanding by example here. This is a very important example, and perhaps the most important, and to Rustam and I is the most interesting example, is the depth function. So Gromov defines the depth invariant of a singular set, and the depth function is central in his definition of this depth invariant. And it turns out that in a lot of contexts, this is a chessboard function. So now we're just looking at maps from an m-dimensional manifold to an n-dimensional Euclidean space of non-negative dimension, smooth and generic. The depth function assigns to each region of regular values a non-negative integer. And this integer that it assigns is the minimal number of self-intersection points of generic paths from a point within the region to quote unquote infinity. And I've defined Gromov's invariant down there if you're interested. But for the depth function here, maybe a picture is better. By infinity, I mean pick any point in the unbounded region of Rn, right? So a picture for R2 here, when you're looking at defining the chessboard function to be the depth, well, pick a region, pick any regular value in that region, take a path from that point to the unbounded region, or what I'm calling infinity, and count the minimal number of times that it intersects the singular set. So the black curves here are denoting my singular set. You can convince yourself any regular values in the unbounded region do not have to intersect the singular set. Any regular values in this region here would have to intersect once to get to infinity. And then you can see 2 for these regions, 3 for this region. The idea is of the depth is kind of, it's the minimal number of intersections you must cross to quote unquote escape to infinity, right? And as you can kind of, again, proof by picture, quote unquote, you can convince yourself that for maps to Rn, the depth is a chessboard function. When you cross a fold curve, you change the depth.
Algebraic depth. So I missed a little. We have no orientation on this curves. Yes.
On the singular set.
On the singular set, we have no orientation.
A priori, no. We actually construct an orientation and co-orientation on our singular set.
And this number C does not depend. It's independent on.
Correct. You have a freedom of choice of these paths in the blue here. The blue paths are the intersections that I'm interested in, which is I'm taking these paths. I just want the minimal of all paths, right? And that's independent of orientation or co-orientation on the singular set.
So this is geometric depth, not algebraic depth.
If you would like to take, well, I'm taking the minimal number. So this would be, yes, geometric depth. Okay, thank you. And a couple of remarks about the depth function, and this is maybe why it's so interesting, is the depth function can be generalized to maps with non-Euclidean targets, where n is just a pointed n manifold. And you take the distinguished point of that n manifold to be infinity. However, when you're looking like for maps to oriented surfaces of non-zero genus, we'll say finite genus still, the depth function is still a function, but it's not a chessboard function. Because, for example, if I cross a fold curve, let's look at this example where f, let's say the image of my singular set is a non-separating curve and I'm mapping to a torus, right? In this context, I could cross a fold curve and go from depth being 0 on this side to depth being 0 on the other side, right? If my distinguished point is some regular value. Well, then, chessboard functions must differ by precisely 1 when you cross a fold curve. And in this context, I do not have that. And so this is precisely the reason thus far that for maps of higher dimension to non-zero genus surfaces, why the problem is still open. because our proof is heavily reliant on chessboard functions, and in this context we don't have a chessboard function. So we and you mentioned orientation and co-orientation via of our singular set, and it turns out that there's a local canonical orientation and co-orientation via chessboard functions. So if we co-orient our singular set, so in this picture, alpha is a curve of the singular set, a subset of the singular set here. We co-orient our singular set in the direction of the region with the smaller chessboard function. So where the region assumes a smaller chessboard value, you co-orient in that direction. And then you orient the singular set such that the orientation followed by the co-orientation agrees with the basis of R2, right? Similarly, for Z2 value chessboard functions, you co-orient towards the region with an even value, or you co-orient towards zeros, and then you orient similarly, right? So the orientation followed by co-orientation agrees with the standard basis of R2. And you can see this is local, right? So when I cross a double point, my co-orientation could possibly flip, because remember, I was looking at the values of the chessboard functions at double points, and there's two different types, right? And so the local canonical orientation and co-orientation from chessboard functions is in no way does it need to agree with the any sort of global orientation you could put on your curve. And so since we have an orientation, we can talk about the cumulative winding number. And you may ask, why does the cumulative winding number come up? Well, we're tasked, remember, to prove this theorem, the idea is we want to have a way of relating the number of circles of the singular set of F with the number of circles of the singular set of G, right? And to relate those, well, we have a mod 2 relationship with a winding number, right? For every circle component, every smoothly embedded component of our singular set, if you were to talk about the rotation number, it would either be +1 or -1, right? So mod 2, the number of components of the singular set, should be the same as the winding number. And so if we could just compare the winding number at the start and end of our homotopy, if we could just compare the winding number of F and G, well, then maybe we could conclude something. The problem is the homotopy in between it is not smoothly embedded, right? There are double points, there are cusps, there's whatever you want there to be. And once you introduce double points and cusps, the winding number is no longer well defined at those double points and at those cusps. So we needed this cumulative winding number, which intuitively is a way of breaking up my singular set into arcs of fold curves. And by an arc, I mean its endpoints are double points and or cusps, or the boundary of the arc is empty, so like a smoothly embedded component. Because you can see in this picture here, if I were to take the winding number, it would not be well defined at this double point. And so I still want to be able to talk about the winding number when I have immersed singular sets. And so we build the cumulative winding number off of the Gauss map here, which you may know the Gauss map just takes a tangent vector. It assigns to each point on the curve its unit tangent vector on S1. If we lift these values in S1 to the universal cover of S1, which is R, then we can get a difference of these lifted values of the Gauss map. And this is what we define the winding number to be, right? It's kind of how far you've traversed along your circle, but it's lifted to R, so we're taking real values. And this is your standard winding number here. And so what we do is we define the cumulative winding number to just be the winding number phi here of all arcs in sigma. Again, so I'm breaking up my singular set into arcs of fold critical points. where again, the endpoints of these arcs are double points and cusps or empty. And so this cumulative winding number allows us to talk about a winding number of our singular set at some moments during the homotopy when it is not smoothly embedded. And so it turns out if all intersecting segments are perpendicular, then so at every double point you perform isotopy on your fold curve so that you have a 90-degree angle, right? Then this cumulative winding number is actually a half integer. And then we have a way of keeping track of the winding number of the singular set throughout homotopy. And so what could possibly change this winding number? Well, what could possibly change this winding number from its initial value, right? The singular set F has some winding number. We start to perform homotopy, and the winding number can change based on the moves we perform. And so we need to record how this winding number is changed. And so I'm quickly here. I see I'm running out of time, so I'd like to speed up a little bit. We record the information of the double point around Reidemeister 2 and Swallowtail moves, the values of the chessboard function in this way, and then we record how omega is changed under homotopy without R3 moves, and because that's what we care about in this context, right? And so you can see here, Swallowtail moves change them by plus or minus a half integer, and then Reidemeister 2 moves change them by plus or minus 1. But what you may notice is these two Reidemeister 2 moves, the double point is of the same type, right? Mod 2, this is the same type of double point. And since we're interested in Z2 valued chessboard functions, these are the same mod 2, these are the same mod 2. And so double points of this type A minus 1, A plus 1, it turns out those don't change the winding number. And so that's very crucial in the proof of the main theorem here. So let's suppose that the dimension of M is even, right? That's the first case. And remember, we're trying to show that the parity of the number of singular set components is preserved. So let's suppose that we're mapping an even dimensional manifold to R2 or S2. The proof for non-zero genus in this case is similar, but for the sake of time, let's just look at the base case here. We'll set C to be the integral Euler chessboard function, which I described earlier, right? When you have a map of an even dimensional manifold to R2 and C is the Euler chessboard function, it turns out that you cannot have double points of type that change the winding number. So the only type of moves that can occur under homotopy don't change the winding number. And here's why. Let's assume that you could have A plus 1, A plus 1 type double point here. Well, let's say without loss of generality, or not, kind of proof by picture is a better way of thinking about this here, or at least with what I've drawn. Let's assume we're mapping a 4-manifold to a 2-manifold in this picture. And the regular fiber in this region is a sphere. Well, if I cross a fold of index 1, or in general, fold of index I, I'm attaching an I handle, right? And so if I were to have a double point of A plus 1, A minus 1, then what would have to happen is I would have to have the regular fiber here is the same as the regular fiber over here. But if I cross this fold curve and attach a 1 handle, well, if I cross that same fold curve, I must still attach a 1 handle, right? And so I can only have double points of type A minus 1, A minus 2, excuse me. And so for like this picture at least gives an idea of the proof for why you can't have double points of this type, which means that the winding number doesn't even change under homotopy when your source manifold is even dimensional. Therefore, since the winding number mod 2 is the same as the number of components does not change mod 2. So when M is odd dimensional and greater than or equal to 3, we can, with no Reidemeister 3 moves, we let C be the Z mod 2 valued depth chessboard function. And then when you're looking at Z mod 2 valued chessboard functions, every double point is of this type, right? Because mod 2, A minus 1 and A plus 1 are the same. And in this context, thanks to Rustum and Ondo, we can assume that no swallowtail moves occurred during our homotopy. In Rustum's chess conjecture paper, he showed that there exists a formal homotopy of F to G with no swallowtail singularities in this context, provided you're mapping an odd dimensional manifold of dimension at least 3 to a surface. And then on top of that, Ondo he gives an explicit method of eliminating those singularity points. So Rustum showed that you can avoid them. Ondo showed that if you have them, you can eliminate them. And so we have the leisure of assuming that no swallowtail moves occur during homotopy. And this is good because swallowtail moves change the winding number by a half integer. And if you're wanting to show that parity is preserved mod 2, you would need a pretty strong statement on the number of swallowtail moves to get your half integers to play nice mod 2. So if we're starting with something embedded, smoothly embedded, and ending with something smoothly embedded, we have to have that all double points that occur in the homotopy are canceled at some point, right? And the moves that are performed, since swallowtail moves are no longer an issue, every move that can be performed changes the number of self-intersections by precisely 2, right? So cusp fold moves either add or remove 2 double points. Reidemeister 2 moves either add or remove 2 double points. And so since we're going from smoothly embedded to smoothly embedded, we must have that the sum of cusp fold and Reidemeister 2 moves is even, right? Otherwise, we won't end up with 0 self-intersections. And so I claim that a stronger statement is true and that the number of cusp fold moves is 0 mod 2. So without loss of generality, let's suppose I and J are of different parity here. So you can see I'm looking at a cusp fold move here. When I perform this cusp fold move, I introduce 2 self-intersections. This intersection is with I and J fold components, and then this intersection appears with I plus 1 and J, right? If you perform a Reidemeister 2 move, both double points are of the same intersecting type. However, for cusp fold moves, they're different. And so if I want to cancel an IJ intersection point, I need another IJ intersection point somewhere. And so the only way that can happen is if my cusp fold move is undone, this precise one, or if there's another cusp fold move of the same type, right? And so that for that reason, there has to be an even number of them. Well, if there's an even number of cusp fold moves, then there's an even number of Reidemeister 2 moves because I have to have that their sum is 0 mod 2. But Reidemeister 2 moves change the winding number precisely by plus or minus 1. So I have an even number of plus 1s or minus 1s. That means the winding number is unchanged, right? The only effect on the winding number under homotopy is an even number of plus 1s or minus 1s and or, right? And then therefore, we have the same conclusion that the winding number is then preserved mod 2. Therefore, the number of components is preserved mod 2. And so I see I'm 5 minutes over time. The proof when H is orientable, or the singular set of the homotopy is orientable, is really not an interesting proof, I'll be honest, to present. The most interesting part is showing that this function that I've written here is showing that this is a Z mod 4 homotopy invariant for orientable singular sets of the homotopy. And once you have that that's invariant, which I here is 2 times the number of components plus the number of cusps plus 2 times the number of self-intersections, mod 4. If you're looking at image simple fold maps, everything is 0 except sigma. And then if you have 2 sigma F is equivalent to 2 sigma G mod 4, well, then that says that the parity is preserved mod 2. So that completes kind of the sketch of the proof to R2. There's a very interesting corollary, which I'm going to forego the proof, which is if you have an image simple fold map from S4 to S2, then it has to have an odd number of components. And so this is kind of a 4-dimensional corollary to Saiki's problem, or a 4-dimensional analog to Saiki's problem that we sought out to answer in the first place. So, and again, I'll forego the proof there. Thank you very much. I'm sorry I went over time slightly.
Thank you very much.
Thank you. Any questions?
Yeah, any questions, I'm happy to answer. I understand it's very late.
What is the philosophy of calculation of the parity of the fold curve?
I'm sorry, could you please?
Originally from it was some kind of invariant, but you can prove that even for the map for map from S3 to S2, a parity is not invariant because we have a very twisted, interesting example. And could you explain just a general looking what we have if we do such a machine for calculation? What kind of problem we can solve using it?
Yeah, what Rustam and I are kind of what we are hoping to do is this invariant, this mod 2 invariant, this should be able to be described, right? We understand that this is a mod 2 invariant, but we don't know precisely what that invariant is. And I think to answer your question, we'll have to figure out more explicitly what this invariant is telling us. Because I don't know if that answers your question really.
So this question is under investigation, or even it is not so important. But anyway, the geometry of fold and cusps are very important, and you may do a lot of progress. I remember we have started with Rustam to learn scientific paper, and now we have much more strong tool.
Yes.
Okay, thank you very much.
Yes. Thank you. Again, I'm very, very grateful for the opportunity to speak. I'm very honored to be a part of the event. So thank you. Thank you.
Any other questions?
Yes.
Okay, if no more questions, let's meet the speaker. So our meeting is over. Thanks everybody for listening and for speaking.
Yeah, thank you. Thank you. Take care, everybody.
So, I think we have to say goodbye now to on the Zoom. Yeah, so goodbye. До свидания. До свидания. Спасибо. Да, благодарить. Спасибо, господа, те, кто пришел на семинар. И я очень благодарен докладчикам и слушателям особенно. Я тоже слушателем был. И особенно я благодарен руководителям семинара Евгению Витальевичу и Сергею Александровичу за организацию нашей работы. Ну и вот можно сказать, что мы немножко стали ближе друг к другу. Будем вместе пытаться разбирать результаты. Спасибо большое. Лев, значит, ты в среду будешь рассказывать, да?
Да.
Очно, да?
Что?
Очно.
Я, может быть, немного приболела, я посмотрю, как возможно.
Ну, хорошо, ладно, ну тогда присылаю дальше.
Хорошо. Всем спасибо.
Ладно, ну.
До свидания. Пока.
До свидания.